Okay, again, I'm going to try and make this video shorter than it maybe could have been, just so it's not super overwhelming. There are tons of examples that you'll have the opportunity to work through, and I want to help out with those individually as you run into them. So I'm just going to run through an overview, show you some proofs of these tests to make sure that they actually work, and we'll get going from there. So the first thing that we're going to do is we're just going to recap. There's 3 types of series so far, like named series that we know about. I want to recap those, what we know, remind us of some examples of those, and get our conclusions going pretty quickly, just so that we have those on the tip of our minds. So when we're applying these comparison tests, we'll know what's going on. Then I want to show you the comparison test. I'll give you a proof of it, and I'll give you some intuition of when you might use this. You could probably guess it's going to have to do with some of the series that we know about. And then we're going to look at something really closely related called the limit comparison test, and we'll show the proof of that, or at least the proof of part of it, the only part that really matters in my mind. And then we'll talk about when to use that. Hopefully this video doesn't get too long with all these proofs. I'll let you kind of pause the video to see details and things like that, so I might not go super slowly through them. So let's first just start with this little recap of some known series types. The first one that we've got is the geometric series. We've got this a r to the k. It normally starts with an index of k equals 0, but we'll find that even if it doesn't, it's no big deal. A is the first term. And r is the ratio. It can be positive or negative. That's no big deal. And as long as the absolute value of r is less than 1, so we're saying things like -1 less than r, which is less than 1. If r is in between those two values, then we know that our series converges, and we specifically know what it converges to. And it diverges otherwise. So if r is bigger than 1 or equal to 1, less than or equal to -1, something like that. So a couple of quick examples that we can do. We're going to get a little crazy, and we're going to look at something like this. We're going to say, oh, wait a second, look, this index doesn't start at 0. Oh, no. No big deal. Let's just write out some terms. This is 1 over 4 squared, so that's 16. Actually, you know what? Yeah, and then I'll leave it like this. I don't know what 4 cubed is off the top of my head. I don't know what 4 to the 4th is off the top of my head. But if I write it this way, I can see a is 1 over 16. R is a 4th. That's small. So our series converges. And specifically, we know our series is equal to a over 1 minus r, which is 1 over 16 over 1 minus a 4th. That's 1 over 16 over 3/4. That's 1 over 16 times 4/3. And that is 1 over 12, right? Cancel that out. Something like this. Cool. So there. This series converges to 1/12. So that's how we can deal with geometric series. Notice it doesn't really matter if r was negative. All that means is that we have some oscillation, right? Positive, negative, positive, negative. We won't call it oscillation so much as alternating because we have these discrete terms instead of continuity going on. But anyways, we'd have this alternating series. No big deal. We would just make sure that r actually is negative, and so you'd notice that you're like adding stuff here when you subtract that negative. No big deal. So that's our geometric series. Hopefully you're relatively familiar with that. The other one that we looked at, or one of the other ones, oh, I forgot an equal sign in here. There we go. I'll try and put that in on the blank version that you guys get. It's a p-series. And this p-series is 1 over k raised to some power. And that's going to converge if p is greater than 1 for big values of p, and it's going to diverge for small values of p. Notice that if p was negative, then we could really just write this as k to the p. And then you're looking at big powers of big numbers. That's obviously going to go off to infinity, and so then we're diverging no matter what. So we normally say, okay, really just look at positive values of p in the denominator, but whatever. So for this, we're mostly thinking about stuff like 1 over k cubed. And notice I'm starting my index at 3 instead of 1. No big deal. all that means is that we're looking at farther into the tail, but you know that the tail of the series is the thing that determines whether it converges or diverges, right? The end of the series. So it doesn't really matter if I miss the first few terms. So I can look at this and say, all right, p is greater than 1. This thing converges. I could rewrite this series as 1 over k to the half. And then I could say, oh, okay, look at this, small p. P is less than or equal to 1, so this thing diverges. Now, with the p-series, we don't know what the convergent ones converge to. For the first couple p-series, with like integer values, I'll say, some of the like really basic ones like k squared and k cubed, you can look those up and find some pretty easy convergent formulas for them, what they actually converge to. There's not a nice formula that says this is what they converge to with regard to p, where you just plug p into the formula. Doesn't work like that. We'll maybe find some convergences of what these are a little bit later this semester, but it's going to take a while. It takes a long time for us to be able to tell what series converge to. So those geometric ones are kind of like a special case where we just were easily able to tell what they converge to. The last type of series that we have is the telescoping series, and there's not really a nice definition for them. Hopefully you just notice it. Okay, there's a bit more than that. What we're looking for here is if you write out the partial sum, some like pairs of terms or maybe combinations of pieces of terms in the partial sum add up to 0. And so whatever your partial sum is, in general, you're left with just a fixed number of terms. A lot of times it ends up being like a first number and then some last term of your partial sum that's in terms of n. And so the whole point is it should make it pretty easy to find this limit. This is what we really care about here. And so if you can find that limit easily, it works out really nicely. So an example might be something like this. I don't know what we've done before, but let's do this. Something really basic like this. We probably did this exact version of it. But the reason that this is nice is that when we write out the partial sum, we have 1 over 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4 all the way up to 1 over n minus 1 over n plus 1. And you'll notice that we have a negative half plus a half, and a negative third plus a third, and a negative fourth plus a fourth, and then eventually we'll have a negative 1 over n plus a 1 over n. And so our partial sum is really just 1 minus 1 over n plus 1. And this makes it really easy to find this limit as n goes to infinity of s sub n, because this is just the limit as n goes to infinity of 1 minus 1 over n plus 1. This second term here we can see is going to go to 0, so this is equal to 1. So we know this series converges to 1. The telescoping series are sometimes hard to work with, sometimes hard to notice, and so we're going to see that those don't show up so much here, which isn't a big deal. If we're familiar with geometric series and p-series, that's going to be all we really need for this section, but hopefully you're familiar with telescoping series. Okay, let's get to the meat of this stuff, the comparison test. Sometimes it's called the direct comparison test. That's mostly to differentiate it from the limit comparison test that we're going to talk about. Let's say we've got two series that we just know what they are. We don't know if they converge or not yet necessarily, but maybe we know some information about one of them. They are only positive terms, so all of the terms here are greater than 0. And this ordering is the thing that we really care about. For all the k values, our b terms are bigger or equal to our a terms. So then, if that's true, if you have these two series where you can compare the term formulas, and we have this inequality, then we'll say that if the b series converges, then so does a. And we'll say if the a series diverges, then so does b. So if we know something about one of these series and we can compare them, we might get lucky and luck into this situation. The main thing to notice is that here we're saying the bigger terms make the series that converges. And so this series is smaller. Oops. than a known convergent series. And this one is bigger than a known divergent series. So if you have something that's smaller than a convergent series, it's going to converge, especially because it's bounded by 0 on the bottom. And if you have something that's bigger than a known divergent series, then it's going to diverge. You can just think of the partial sums if you want to visualize this, but let's run through the proof. I'm going to go through this relatively quickly. It's going to be dealing with the partial sums, and feel free to go back and read through this. You're not responsible for the proof, but this is hopefully just to build a little bit of intuition about why this is actually true. So let's just let these things be two series with positive terms for all these relevant values of k, and we have this ordering. Then let's take a look at the partial sums. Okay, so we're going to call S sub n the partial sum for the A series, and we're going to call T sub n the partial sum for the B series. Since we know that we have this ordering of terms here, we know that all of these values are smaller than all of these values. And if you add up a bunch of smaller numbers, compare that to adding up a bunch of bigger numbers, the sum of the smaller numbers is going to be smaller. Hopefully that makes sense. So we know we have this ordering of partial sums because we have all these smaller terms compared to all these bigger terms. Also, since they're all positive, we know that the partial sums, both of these things, are increasing sequences. What do I mean by that? Okay, so think about what happens as n gets bigger, or essentially what happens when you add more terms to both of these. Well, you're adding more positive terms, and so each of these partial sums is going to get larger. You're not getting smaller because you're not adding negative stuff. We have positive terms always. So even if it's not getting bigger by a lot, it's still increasing. All right, so you can maybe see where we're going here. Our sequences are increasing, so we could say they're monotonic. So what we're going to want to show is some things with maybe boundedness. There we go. Let's take a look at two parts. The first part is we're going to assume that B series converges, because remember, we're going to say, all right, if B converges, hopefully we'll show A converges as well. So we know that if this series converges, then that means the sequence of partial sums has to converge. And if we know that converges, that means that this limit exists. So t is just some real number that this sequence of partial sums converges to. So we can say, all right, that's really what this series converges to. If it converges, there's a real number that it adds up to. That's what the limit of the partial sums goes to. Also, since we had this inequality from before, we know that as n gets bigger, this thing is going to go to t. And so for all the values of n, this other partial sum has got to be less than or equal to t. And so that means that our sequence is bounded above. So it's bounded because our partial sum is going to exist between 0 and t. Now we knew that it was increasing, so it's monotonic, and now we know that it's bounded. That means this sequence of partial sums, S sub n, which we didn't know much about, it has to converge. And so also our series converges. We don't know what it converges to. Here we had this one converging to t, and here this one equals something. We don't know. But we know that it converges. For the second part, we're going to do something kind of similar. We're going to assume that this A series diverges, and we're going to try and show that the B series diverges as well. Since all the terms are positive, we know that the partial sum is still increasing. That's still true. Since this diverges our series, we also know that our sequence of partial sums has to diverge. If it didn't, then we'd know that the sum converged, but that's not what we have setting up. We're saying, no, this series here has to diverge. We're forcing it to. So that means that this sequence of partial sums has to diverge, and so that means it can't be bounded, because if it was, we have that it's monotonic and bounded, and so it must converge. So it can't be bounded for this thing to diverge. That means that if it's unbounded and positive, it's going to be increasing. We know that it's increasing. It can only go up to infinity. Positive, increasing forever. It's going off to infinity. Now, it actually doesn't look like that. It looks more like this. Right? Because it's got these discrete points. But whatever. So, now what we can do is say, well, wait a second. Our t partial sum we said was bigger than our s partial sum. And that means that if that's going to be true for all these values of n, as n goes to infinity, t has to be bigger than this here. That means t also has to go to infinity. So the sequence of partial sums t diverges, and that means this series also diverges. So what we've just shown is that if one of the series converges, and we have another series that's less than that convergent series, it also converges. Or if one of the series diverges and the other series is bigger than that divergent series, it also has to diverge. And that's the comparison test. Okay, so how the heck do we actually use this? When does this show up? We're going to go back to those known series, and we're just going to look at these and say, well, do these kind of look like some known series? My calculus professor, when I was an undergrad, used to always talk about using fuzzy goggles or blurry vision here. And not actually, she didn't really mean like squint your eyes and make this blurry or take off your glasses so you can't really see what's going on. What she meant was figure out what are the dominating pieces here. Specifically, this +2, does it really mean much? When k gets really, 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 really big, is adding 2 to this 3 to the k going to do much? No, not really. The dominating feature is this 3 to the k in the denominator, right? That's the part that really matters. And so let's compare this to just 1 over 3 to the k. Would you look at that? We could really write this as a third to the k, and bang, this is geometric. So let's do a little comparison here. Let's say 3 to the k plus 2 is bigger than 3 to the k. That means 1 over 3 to the k plus 2 is less than 1 over 3 to the k. And that means this. We can order our series in the same kind of inequality. The series of 1 over 3 to the k is less than this convergent geometric series. And so we know this thing has to converge by the comparison test. Let's take a look at this version as well. Here, the k is the only thing that matters. So let's compare to the sum from k equals 21 up to infinity of 1 over the square root k. And hey, isn't that a p-series? Oops, this is supposed to be 21 up to infinity of 1 over k to the half. That's a divergent p-series. We can notice this has a smaller denominator than this one. And so that means that if we have a smaller denominator, it's actually bigger. So the series we're looking at is bigger than a divergent p-series. So I'll let you string together the inequalities like we did here. But there we go. And this one, notice that what we really care about is just this square root of k and this k. And so we could say, let's compare it to the series from k equals 1 up to infinity of 1 over k times the square root of k. But that is really 1 over k to the 3 halves. And that's a convergent p-series. This denominator is a little bit bigger than this one, because k plus 2 is bigger than k. So the square root of k plus 2 has to be bigger than the square root of k. And so the whole denominator has to be bigger. And so that means the terms are smaller. Bigger denominators are smaller fractions. And so you have a smaller series than a convergent p-series. Things work out great. I'll let you fill in all the details. There's tons of examples that you can look at later. But this is in general what's going on. Okay, so the limit comparison test. Let's talk about what that is, how it's a little bit different when we use it. So this is a little crazy. So let's say we've got these two series, still positive terms, but now we don't really care too much about the ordering yet of them. We don't care if one of them is bigger yet. What we're going to say is let's look at this ratio, and let's take a limit of this ratio. We're going to say it's equal to L. Now, L might be a real number, might not. In this first case, we're going to say L is some positive real number. It's a finite value bigger than 0. Now, notice that it can't be a negative value, because that would mean that a numerator or a denominator here had to be negative, and that can't be true with positive terms. We will notice that L could be 0, but we'll talk about that in a second. So if L is some positive real number, then the two series, they both converge or diverge together. So if you know something about one, you know the exact same thing about the other. That's cool. If L is equal to 0 and the denominator series converges, then that means the numerator series converges as well. We'll unpack this a bit in a second. And if this limit goes to infinity, actually, and the numerator diverges, that means the denominator diverges as well. All right, cool. Let's talk about these two here. These two specifically, these are just the comparison test. Think about what needs to be true if this limit is 0. For number 2, if the limit is 0, that means our denominator has to be really, really big compared to our numerator. I'm going to use a double inequality to say really big. And that means we've got this nice inequality where this thing converges. A series converges. So does the series of a sub k. This is just the comparison test, right? Because we've got this little inequality here. In number 3, we'll say if L is equal to infinity, what does that mean? That means the numerator has to be really, really, really big compared to the denominator. All right, did I get this wrong? Yeah, I wrote this wrong. This is supposed to be b sub k, and this one is supposed to be a sub k. I'll change that on your values here. Then we can say if the sum b sub k diverges, then our a1 is bigger than a divergent series, so it converges as well. So number 2 and number 3 are really just the comparison test. Number 1 is the thing that we actually care about. So this is the important piece that we're going to actually deal with. So I'm only going to prove this. Oops, where's my highlighter? There we go. I'm only going to prove this version of it because this is the one that really matters. And then, again, I'll make that little update on your blank slides so you'll have it right. My bad for the typo. All right, so let's prove the limit comparison test, but really we're just going to care about part 1. This is a little bit weird, but that's okay. So we've got both of these terms that are positive for k equals 1, 2, 3, up, blah, 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 blah. And we're going to let this ratio be L for some positive real number, L. So again, we're thinking about this case here. That was our first case. So some finite positive value. That means that we can take this here and we can say if A over B is equal to L, then if we look at 1.5 of L's, that should be too big. And if we look at just half of L, that should be too small. So that's what this inequality is doing. Now, this is true for large enough values of our index. I think I put this in here. K bigger than some positive capital K, some large value. I think I put that in later. Again, maybe I'll try and fix that on your notes so that you've got it written in there. Then we can say, oh yeah, here it is. All right, I'll fix that later. Then we can say we have some bounds on a sub k by just multiplying this on both sides. So that's what I've done on this version here. I've just multiplied this b sub k, and so it goes on both inequalities. It doesn't change the direction of the inequalities since it's positive, since we know that we have these positive terms, and multiplying by a positive number just keeps the inequality sign in the correct order, or in the same order. And let's say that this is true for all the k bigger than some capital K, where this is just some big index. Then we can apply the comparison test to show that these two series act the same. So here we go. First, let's pretend that our B series converges. We're going to show that A converges as well. So for large enough K values, K greater than this capital K, we have just this part of the inequality that I care about. The reason I care about this is because I know this thing converges, and so I want to use the comparison test, and I want to look at something smaller than it. All right, so the ordering of these series acts the same way. Notice I'm only starting my index at this value of K, this large index. I'm saying everything before then, the ordering might be a little bit off, who knows, but at least after that, we've got this ordering. By the comparison test, then, we have one series smaller than a convergent series times some real number here. And notice that this number is positive, so it doesn't change the sign of anything, doesn't screw anything up. So that means that if the whole series B sub k converges, then so does A sub k, because this series has to converge. Now notice, in this one I have my index starting at capital K, and here I could start at like k equals 1 up to infinity. Because all the beginning terms don't really impact convergence or divergence, it's just the ending terms. It's just the stuff really far into our series that impacts convergence or divergence. We're going to do the same kind of thing. Let's assume that our series B diverges. We'll just use the other half of the inequality. So we'll say, all right, we've got this comparison of series. By the comparison test, we know this thing diverges. Oh my gosh, I keep hitting the eraser on accident. There we go. And so our series is bigger than a divergent series, so it also diverges. If the tail of our series diverges, then so does this one. So what we've shown is that if L is just a positive finite value, then these two series converge or diverge together. All right, so when do we actually use this? These three series are very, very similar to the other examples that we looked at. But notice this used to be a plus, this used to be a minus, and this used to be a plus. So what this means now is that if we look at 3k minus 2, that's less than 3 to the k. And that means 1 over 3 to the k minus 2 is greater than 1 over 3 to the k. And that means our series 1 over 3 to the k minus 2 is greater than our series 1 over 3 to the k. And now this is bad, because our comparison test says that, hey, if this thing converges, if our inequality was less than here, we'd have something less than a convergent series, then it also converges. But now we have something bigger than a convergent series. Well, if this is bigger than a convergent series, maybe it converges, but maybe it's bigger than a convergent series because it goes off to infinity, right? And so we don't know anything. So our comparison test here fails because the inequality is set up in the wrong way. But our intuition probably still says this is essentially a geometric series, right? This minus 2 we said wasn't going to do anything later on. So what we could really do then is say, well, let's just use the limit comparison test. Set up a limit of a ratio of these, and you're going to show that these act exactly the same, because the limit is going to end up being 1. So what you're going to look at is a limit as n goes to infinity of 1 over 3 to the k minus 2 over 1 over 3 to the k. This is really a limit as k goes to infinity of 3 to the k over 3 to the k minus 2. You can use L'Hopital's rule on this really easily. I'll let you fill in the gaps to show that this is 1. That means these two series act the same. Since this one converges, so does this one. Do the same thing for your other two series. Mess around with those. See if you can compare them to the same P series that we compared them to before, but use the limit comparison test. And that should help quite a bit, I think. That's all I've got for this video. That still ended up being a long one, but I didn't go into depth in these examples. There are tons of other examples out there. If you need help setting up comparisons or knowing what to compare to, just ask. Those are things that we can go over in office hours. I can put up some more posts and stuff like that on Canvas to help out. But that's the part that's going to be hard, building up the intuition to figure out what are we comparing things to. And if our comparison test fails, how do we set that limit comparison test up, still using our intuition? Good luck. Let me know if you have any questions. Hopefully that's helpful.